Hi everyone, and welcome to another video of this channel. So today we will investigate the principle of inclusion exclusion, which is a principle in probability, and we will also look at a very interesting problem called the Montmort problem. So let's get started with the principle of inclusion exclusion. And just to introduce this principle, I'm going to draw this picture right here. So this picture means that, we have a sample space S, right? And the sample space is basically the set of all possible outcomes. We're talking about probability here. And then we have an event A, represented by this circle, and an event B. And then their intersection is A intersect B, which is denoted like this. So now, let's suppose that we want to calculate the probability of A or B happening, right? A or B is also called A union B. So just basically this thing right here. Well, how would we calculate that? Well, at first you may think that it can be calculated like this. So we just add this big circle, add this big circle. But the problem is that this football-shaped intersection, right? A intersect B, it's counted once here, it's counted another time here, so it's counted twice, not once. So we have to subtract the probability of this intersection right here. And I want to make a quick distinction before we move on. This A is the event A, and then this P of is the probability of this event A happening. So basically, this is the really simple case of inclusion exclusion for two events. So now I'm going to demonstrate it on three events. Well, suppose we have three events, A, B, and C. Now let's label all the intersections, right? So the intersection of A and B is this football-shaped region right here, including this triangle. And then the same thing can be said for the intersection of B and C and the intersection of A and C. And then this little triangle right here, this is the intersection of all three events. So now, let's suppose we want to find the probability of A or B or C happening, right? A union B, union C. So this probability can be represented just like this, P of A union B union C. So just as in this example, first, in order to calculate this probability, we add the probabilities of each individual event, right? P of A plus P of B plus P of C. The problem is that when we add P of A and P of B, right, just as in this example, the probability of this football-shaped event happening, right, is counted twice. We want to count it once, so we subtract P intersection B. The same goes for the intersection of C and B. We count it twice, so we must subtract it. And for A and C, this also applies. But then let's just look at this triangle region, right? So in this sum right here, it's added 3 times, right? Since it is a subset of A, B, and C. In here, it's subtracted 3 times, right? Since it's a subset of A intersect C, A intersect B, and B intersect C. So it's added 3 times, subtracted 3 times. It's not counted at all. We need to add it back in. And so basically, from this case, we can look at a general formula. And this general formula is, well, what if we want to find the probability of the union of n events, right? A1, A2, all the way to AN. Well, that will be first the sum of the probabilities of all the individual events. Then we subtract from that the sum of all the probabilities of all the intersections of each 2 events taken in pairs. And basically, it's this alternating pattern right here. And this is general formula. Now, this is not definitely something you have to memorize. In fact, if you just memorize this 3-case example right here, this case where we have 3 events, it will all just fall in place. So basically, it's this alternating pattern. Okay, so that's inclusion exclusion, which is once again very useful for finding probabilities of unions. So now we will look at a very interesting application of this inclusion exclusion principle. It's called the Montmort's problem, also called the Montmort's matching problem. And I first came across this in a Harvard statistics and probability course. I'm going to post a link in the description about it. It's a really good course if you want to really dig deep into probability. And just a little bit of background on this problem. Basically, de Montmort, right? He lived in the early 18th century, and basically a lot of probability that was done around that time was related to gambling. And basically, de Montmort's problem is also about a card game. So let's suppose we have n cards, right, like this, and we put giant labels on them, 1 through n. Then we shuffle the cards, right? So suppose like this. For instance, right, this is just one possible arrangement. And then we put these, basically we shuffle these cards into a deck, and then we flip over each card one by one, right? So we flip over the cards, and as we flip each card, we say the numbers 1 through n. So as we flip over this first card, we say the number 1. As we flip over the second card, we say the number 2, and so on. And then when we flip over the nth card, we say the number n. Now, you see here how on the second turn, right, when we said the number 2, the card with a big red number 2 appeared. And so when this happens, this is a match. And if this happens at any point in the game, we win. If it doesn't, we lose. And so de Montmort wanted to find out what is the probability of winning. And so basically, to answer this question, we first define events, and let's call the events AI. So AI, basically A sub I, is the event that when you say the number I, the card with the big red letter I pops up. And once again, AI is not the probability of this happening, it's just the event that this happens. So the probability of this happening would be P of AI. Now, our goal is to find this right here. Now, why is this our goal? Well, this right here, right, A1 union, A2 union, and all the way to union AN, this represents the event of the first card matching, or the second card matching, or the third card matching, and so on until or the nth card matching, which is exactly what we want to find. And so this, we can just use inclusion exclusion, right? In fact, we can just directly copy and paste the general formula. So basically, we add up the probabilities of each individual event, then we subtract the probabilities of the intersections of each event taken in pairs, and then we add -1 to the n plus first power times p of all of the events intersected. So now, one interesting thing we can notice is there is no reason for the first card matching to be more likely than the second card matching or the 11th card matching, right? There is no reason for that to happen. And therefore, we can say that P of A1 is equal to P of A2, which is equal to P of AN. Similarly, P of A1 intersection A2, there is no reason for that to be less likely than P of A1 intersect A3. So all of these are equal. And basically, etc. We could just say this for all of the terms in this inclusion exclusion. So then we can set this probability equal to, basically all of this can be written as n times P of A1, right? Because there are n events and red of P probabilities added up, and each one is equal to P of A1 by this right here. And then basically we can say the same exact thing for these blue events. There are n choose 2 blue events, right? And then we can multiply that by the probability of A1 intersect A2. And basically so on. Now let's find the probability of A1. And basically how do we do that? Well, we want the first card to, when we flip over the first card, we want to say the number 1, right? So we want this big letter 1 written on here, right? So basically, how can we think about it? Well, think about it like this. We fix the first card in place, and then we let the other n-1 cards just move around however they want. And so basically, we can use, since all the probabilities here are equally likely, we can use the favorable outcomes over total outcomes formula. And there are, in all, n factorial total ways to reorder the cards. And for favorable outcomes, we want to keep this first card in place and reorder all the n-1 factorial cards. So then P of A1 is n-1 factorial over n factorial. The same exact thing goes for P of A1 intersect A2. It's n-2 factorial over n factorial, because we fix these two cards in place, and then we move around the other n-2 cards. And then basically, it's the same thing, all the way up to the probability of all the intersections case. But now, a really interesting cancellation happens. Notice that we can simplify it like this. Right? So n choose 2, this term right here, that's equal to this right here. And then we pull this term right here. And then let's say that we want to take the intersection of 3 events, right? And the same exact things happen here. Basically so on to the nth case. So now look how all of this stuff cancels, right? So this n and the 1 over n cancels, this n factorial and the n-2 factorial, they all cancel. Basically everything cancels here. And all that is left is that this probability of A1 or A2 or A3 all the way to or an happening is 1 minus 1 over 2 factorial plus 1 over 3 factorial, and basically so on to negative 1 to the n plus 1 over n factorial. So now this, if you know Taylor series, this should definitely ring a bell. And through Taylor series, we know that the Taylor series for e to the negative first power is equal to 1 minus 1 over 1 factorial plus 1 over 2 factorial minus 1 over 3 factorial, and so on. So then this sum right here is 1 minus this. And so this sum right here is approximately equal to 1 minus 1 over e. Again, approximately, because this is an infinite sum, and this sum right here has n terms, which is finite. And then this right here is equal to 0.632121. So I find this result incredibly fascinating because, firstly, this is a bit counterintuitive. Because most people, I haven't done a formal referendum or anything like that, but most people, when they say, okay, what is this probability when n is extremely large, right? When n blows up a million, a billion, and etc., they will usually say, okay, so it's either 0 because it's so unlikely for each card to be matching, or they will say 1 because there are so many cards. And these two forces eventually balance out to 0.632121, 1 minus 1 over e. And 1 over e is really, it's really fundamental in probability, especially since this sum appears a lot. But the other reason why I find this result incredibly amazing is because of how fast this thing converges. So I'm just going to do a quick demonstration here. So for this quick demonstration, basically what I have here is the sum, right, that we approximated the Montmort's problem with, and basically it's evaluated up onto n. And then here I have the values of n, right? So f from n equals 1 to 52. So we'll see how fast the sum converges. And then here I have the actual value of 1 minus 1 over 8, right? That's our approximation for the answer for the Montmort's problem. That's our probability approximation. So now, for n equals 1, of course, the sum is equal to 1. Then at n equals 2, there's also nothing special. But then at n equals 3, it starts converging. n equals 4, n equals 5 is already corrected 2 decimal places. So then at n equals 10, it's already corrected 7 decimal places. So at n equals 10, this is already less than a 1 millionth error. But then it really quickly converges as n gets really large. So then by n equals 5, I mean, and by n equals 15, um, there's no difference as shown on the calculator. Of course, there is like a really small difference, but this sum is correct to 12 decimal places or something. So this approximation is a really good approximation. So thank you for watching, and I'll see you next time.